The journey from abstract mathematical theory to interactive 3D visualization is a structured process that bridges the gap between the derivation sheet and computational rendering. This progression is best understood through two lenses: the conceptual roadmap of the demos and the technical workflow that brings them to life. The conceptual journey. State diagram. The state diagram illustrates a purposeful progression where each demo serves as a prerequisite for the next, mirroring the logical flow found in the derivation sheet. Establishing the foundation. The narrative begins by defining the intrinsic properties of the position vector, specifically how it expands outward from a central point. Defining the zero baseline. Building on this, the next stage establishes the null identities. These are essential building blocks that visually prove which types of field movements, such as specific rotations or cross-product flows, effectively vanish or cancel out across the entire volume. Decomposing flux and flow. Once these constants are established, the complexity increases. The focus shifts to how a field interacts with its own rate of change. This stage breaks down complex flux into simpler components, specifically looking at how the intensity of a field's change relates to its second-order spatial variations. The final synthesis. The final stage integrates all previous lessons: expansion, null properties, and flux decomposition. It introduces the concept of directional changes along the position vector, culminating in a visualization of intricate rotations and complex vector flows. The technical execution. Sequence diagram. While the state diagram explains why the demos follow a certain order, the sequence diagram outlines the precise algorithmic steps taken to translate the derivation sheet into a visual experience. 1. Initialization and grid setup. The process starts by defining a smooth, 3D cloud-like field and calculating its various rates of change. A virtual three-dimensional grid is then established to serve as the stage for the evaluation. 2. Mathematical evaluation. The system takes the identities derived on the derivation sheet and computes their values at every single point within the 3D grid. For complex identities involving directional flow, the system organizes these into distinct spatial components to ensure the movement is rendered accurately. 3. Animation and rendering. Finally, the visualizer cycles through these calculated terms frame by frame. This allows the viewer to see how individual mathematical parts, such as the field's gradient or its second-order Laplacian change, combine to form the total identity. 4. Visual mapping. Depending on what is being shown, the system chooses the best visual tool. Scatterplots use color to show intensity or magnitude, while quiver plots use arrows to reveal the actual direction and flow of the vector forces.